Hello, George Romanic here. Today we are going to talk about the equation of state for an ideal gas. Equation of state is an equation that relates three main macroscopic properties of a gas: pressure, temperature, volume. In previous videos, we defined properly the concepts of temperature and pressure, and volume is trivial. The equation of state says that these three quantities are related in an ideal gas, and we say that pressure times volume is equal number of atoms in that volume times universal constant called Boltzmann constant times absolute temperature of the gas. Equation of state is very applicable to many gases such as air, helium, hydrogen, oxygen, whichever one, at typical pressures and temperatures that we experience in our surroundings. It is one of the fundamental equations in atmospheric sciences and engineering. However, equation of state for an ideal gas has several forms. All of them at the same time represent the behavior of an ideal gas. But there are three main forms of the equation of state that are important, and depending on what you are studying and what is the problem you are dealing with, you should know which one of these three forms is most applicable to your particular topic of interest. So now we will start from the basic fundamental form of the equation of state for an ideal gas and derive two alternative forms, and in particular the third form that I will talk about, that includes density of a gas, is very applicable to atmospheric sciences. Let's do it. In my previous videos on pressure and temperature, we derived the expressions that pressure times volume is equal N times 2 over 3 times the average kinetic energy in the gas, which is mv squared over 2 everything averaged. And in my video on temperature, we define temperature as 2 over 3 times 1 over k times average of 1 over 2 mv squared. So, if we combine these two expressions, we will get that P times V is equal NKT. And this is equation of state for ideal gas. Here, P is pressure of the gas, and it is given in pascals. V is volume that the gas occupies, and it is given in cubic meters. N is the number of atoms in this volume V, and this quantity doesn't have units. K is Boltzmann constant. The value is 1.38 times 10 to negative 23, and units are joule per Kelvin. So Boltzmann constant gives us the relationship between energy, which is joules, and absolute temperature in kelvins. And lastly, T is absolute temperature. And you have to use kelvins in this equation over here. Equation of state for ideal gas is the pinnacle of the kinetic theory of gases. Now, if you look into this equation, you can see something amazing. If we know temperature, pressure, and volume that the gas occupies, we can calculate the number of atoms in the gas. And that's what we are going to do now for my room. Before this video, I did measurements and I noticed that my room which is approximately square, has width of 2.5 meters, length of 4 meters, and height of 2.7 meters. It's a high ceiling room. And there are all kinds of atoms in the air in my room. Temperature in my room is 22 degrees Celsius. But remember, I have to move this in kelvins, so that is 295 kelvins. Pressure in my room I measured is 1016 millibars, and that will be 1016 hectopascals, and that is 1016, and hecto is 2 more zeros, pascals. Boltzmann constant is right here. So from this we can calculate that the volume is multiplying these three numbers, approximately 26 cubic meters. Or from here we can see from our equation of state expressed in terms of n that n number of atoms in my room is PV divided by KT. And if you plug in all these numbers, you will get approximately 6.5 times 10 to power 26 atoms. This is a huge number. 1 trillion is 10 to 12, I believe. So this is more than a trillion atoms in my room. Just amazing. And we calculated all this using our simple equation of state. And as Richard Feynman points out in his first book on physics, all this is possible because of Newton's law of motion. Because, remember, we derived particularly these two expressions using only conservation of momentum, conservation of energy, Newton's laws, and so on. So the entire thing depends on classical physics and Newton's laws. So this equation is, we could say, the source form, the original form of the equation of state, the most fundamental form. But then something happened. Chemists said, we don't like this equation, PV equals NKT. We don't like it because n is too large number or k is too small number, and we don't like working with these large and small numbers. So what they said, we will invent something called 1 mole. And that 1 mole is 6.02 times 10 to power 23 of anything. So 1 mole of atoms is this many atoms. 1 mole of tractors is this many tractors, and so on. And this number has name, it's called Na, Avogadro's number. The exact value of the number is also very arbitrary, and 1 mole, which is this number, is defined so that 1 mole of carbon atoms of isotope 12 is exactly 12 grams. So what I'm saying is 1 mole of carbon atoms, isotope 12, equals 12 grams. Very, very arbitrary. By the way, isotope C12 means 6 protons in the nucleus plus 6 neutrons. But then, with this arbitrary measure, they said, well, this number of atoms in the volume V can be expressed as the number of moles times the number of atoms in 1 mole, which is this Avogadro's number. Well, that means that our equation of state becomes instead of n, I write NNA times k times t. But both of these are now constants, and we call this another constant, usually R star, and that is called universal gas constant, and the value is just multiplying these two numbers, 8.317 joule per mole per Kelvin. And consequently, the equation of state becomes PV is equal N R star T. I believe that this equation of state is sacrilege because number of moles is completely something that is not intuitive. There are between 100 and 375 people on this planet that have very good intuition of 1 mole and so on. But here, number of atoms in volume V is very intuitive, despite the fact it's huge, enormous number, but we know what it represents. It's number of particles, number of atoms. Here we have some number of moles, and all students are struggling with moles, and then you need to remember this whole thing and so on. So it's a mess. You see, it would be like, if you look into this equation over here, let's say you have 6 objects, and perhaps you ask a physicist, Boltzmann or Maxwell, that contributed to developing this equation, how many objects is here? They would tell you it's 6. But based on this, chemists would tell you it's not 6. It's 3 pairs of 2. I will define something called pair, and then total number of objects is number of pairs times number of objects in one pair. So you see, based on my calculation for the number of atoms in my room, I could say that it's a new constant, Nr, called Romanic number, and that is number of atoms in my room. And therefore I could say that PV is equal, well, instead of N, I will write number of atoms in Romanic room times number of Romanic rooms times K times T. But K, Boltzmann constant, and Romanic constant are both constants, and I will call it R2 stars, universal Romanic constant. So PV becomes N R2 stars times T. And this is now equation of state for ideal gas based on the Romanic principle related to the number of atoms in my room. Now we can say a few more things about this number of moles. Number of moles, N, is also equal mass of the gas divided by the molar mass of this gas, where M is given in kilograms. That's simply mass of the mass of the gas if you would measure it, and molar mass is kilogram per mole. So if we take this N and plug it in, not in Romanic, but in this version of the equation of state, then we will get that PV is equal M divided by M R star times T. I will rewrite this as P is equal volume. I will move to the other side. So I will get mass divided by volume, R star divided by M times T. But notice that this over here is constant for a given gas, which means, so it's not universal constant like this, but for a given gas, this M is constant. So I could say that therefore P is equal M divided by V, that is density, mass over volume. This is just called R, not R star, this is called R, gas constant, and T is temperature in kelvins. And this is equation of state expressed using density. And this, in fact, is the most common form of the equation of state that we use in atmospheric sciences. Because we don't like density in atmospheric sciences, I said it many times on this channel, and whenever we encounter density, we can eliminate density using this form of the equation of state, because clearly from here density is pressure divided by R times T. And R is gas constant. For dry air, we say RD, that's dry air. The value is equal to 287.053 joule per Kelvin per kilogram. If the air is dry, we would say P is equal rho RdT. And dry air simply means there is no water vapor. And we will see in future videos why we want to separate water vapor from other gases in a parcel of air. Equation of state is one of the fundamental equations in atmospheric sciences and engineering. It is unavoidable if you are interested in studying these topics. You cannot properly understand the air and the dynamics and thermodynamics of the atmosphere if you are not familiar with the equation of state for an ideal gas. Fortunately, nature was generous, so she gave us an equation that is very simple to remember. Pressure is equal density times gas constant for that particular gas times absolute temperature. It doesn't get simpler than that. So I suggest, instead of remembering Handel for some beauty blogger or how to mix something to create perfect makeup, you devote your attention to studying equation of state, ideal gases, and atmospheric sciences. Until next video, goodbye.